All right, so TCPIP. As I was just saying, this is going to be a bit of a review from our last class. We are going to go into a bit more depth on things. We have already talked about things like IP addresses and MAC addresses and binary and all those things, but we're going to come back through those today because, well, I got ahead of myself. That's sometimes how it works. But anyway, first things first. When we're dealing with things that are TCP/IP, is network interface cards. All right. Over here on the right, I've got a plethora of network interface cards. Okay. And we've kind of talked again previously. You kind of have like two options mainly. You've got a wired and a wireless connection. Right? And there's in each of those categories, there's again kind of two options. In the wired category, you either have traditionally Ethernet or fiber optic. Basically, everyone that doesn't need stupid amounts of data is going Ethernet. If you're going like a big server or something, then fiber optic might be how you're going. Or if you're going to go wireless, you have the traditional Wi-Fi, what we have going on here. And the other option I have up on the screen is cellular. You can go directly to a cellular connection. All right. Some people, if you live out in the boonies, that might be the only option to have, pay T-Mobile or Verizon or whatever for internet at your home over their wireless connection. So that's a cellular connection that we then most likely convert to Wi-Fi. But in your cell phone, if you have a data plan, that is just, you have your Wi-Fi off, just using your cellular data connection. So it really, kind of comes down to a little left and right, whatever you want to go with. But there's a lot of options. So on the screen, I've got a whole bunch of different devices. So if we want to just go ahead and start with this top one up here. Let's see if this is going to draw. I'm going to draw when there's other stuff in my way. There we go. That's a wonderful line. That's okay. This would be a gigabit NIC, Ethernet NIC, as it says. If you don't remember, NIC, Network Interface Card. All right. This one happens to be by the wonderful brand of D-Link. I don't really know how wonderful it is, but and this one happens to be using what's called a PCI connection, which we will talk more about on the next slide or next slide. But this would be something that you'd plug in internally on your computer, traditionally a desktop. I think old laptops actually used to have a PCI slot that you could like slide a card into. I remember I had a device that had, I think it was an Ethernet plug that if you wanted it was Wi-Fi. If you wanted Wi-Fi, you had to slide this thing in. It was, the card slot was probably 2 inches wide or something, but really freaking skinny, maybe like only 1/8 of an inch or something. You just slid this thing in, and I'm pretty sure that was a PCI slot. But, modern laptops, you don't have access to PCI slots really. Maybe internally, that's going to be like a little micro one, like for a Wi-Fi card or something like that. But overall, you don't really have access to PCI slots on laptops. But desktops is a great option for adding networking. Down here, we have another PCI slot. Now, if you notice, this one is a lot shorter than the one up here. All right, so just two different options. This one, though, is our wireless. I'm assuming this is wireless. I mean, it's wireless. I'm just assuming it's Wi-Fi. It could be cellular, but most likely looking at that, I'm going to assume it's a Wi-Fi, and especially since it's for a PCI slot, again, desktop. You don't normally think about having a cellular modem desktop. Not saying it's not possible, just you don't traditionally think about it. At least I don't traditionally think about it. That one's Wi-Fi. Oh, that's wonderful. Anyway. Over here at the bottom, again, we have another PCI, as you can see that one. Now this one has a bit of a funkier connection to it. All right. This is another network card. It's not traditional Ethernet though. This is designed to actually have this other device right here slotted into that square. And then this is fiber optic. All right. So this is the adapter card that takes the electrical signals in, and I'm pretty sure it throws them out to this, and then this actually takes those electrical signals and converts them to light, or reads light and converts them to electrical, depending on which of these ports it is that you're using. So that one I believe is actually fiber optic. Up here we have a USB Ethernet adapter. I do happen to have one of those bad boys just hanging out here on my desk. I want 3. Talk about more in a minute. But anyway, basically the one on the screen, the one I right there, probably exactly the same thing. Nowadays, USB has kind of taken over, I would say, for interfacing things to your computer. I can do anything with it at this point. It used to be like, oh, you wanted to do that? Oh, you need to use FireWire. Oh, you want to do that? You need DisplayPort, or whatever the case is. At this point, though, like USB 3 has somewhat taken over. It's not an end-all be-all by any means, but when it comes to the world of PCI versus USB, PCI used to be the king. It's a peripheral component interconnect, and down here in the bottom corner, you can see that there are really, I'm going to call them 3 different slots. All right, this AGP, we don't need to, not going to worry about that one. I think that was like something GPU or something. An older connection that we're not really worried about anymore. But anyway, that used to be king. And if we look up here in the PCI Express, so that's about a gigabit per second. And now we are in the PCI Express world. I think everything is running PCI Express. And if you look at that, because PCI versus PCI 1, Express 1, 12 gigs for PCI 1. So that's a nice little difference there. But that PCI Express 1 is just the standard. Nowadays, remember how we saw those different size cards? These. The connections actually plug into the computer. That's because we have different width slots. So here you can see we have by 4, by 8, by 16. Right? And we've started, and then when we get to PCI Express 3, we go down to a by 1 lane, actually. But you can see our different speeds. So for a PCI 2, that's 4 lanes wide, it's 4 gig. For 16 wide, 16 lanes, it's 16 gigabits. So we've now gotten a boatload of speed that we can. 16 gigs is a freaking lot in the long run. So a big benefit there. Especially the capability to say, okay, we need 4 lanes or 1 lane or 2 lanes or whatever the magic is. I believe it's 1, 4, 8, or 6. I don't think there's an option. And you can plug a 1-lane device into the 16 slot. If you had that really skinny little connector that was only like this, you could plug it into that slot. It would work just fine. You just wouldn't be accessing all of these lanes that are over here. So it really just depends on the situation you're in of what you're trying to use and whatnot. Traditionally, your GPU is one of the few things that needs the full 16 lanes of data communication. Maybe if you're doing a lot of hard drive access with RAID cards and things like that, you might need a bigger slot. But like for Ethernet or things like that, I mean, PCI 3 1X slot, that's 2 gigabits per second that we can transmit over that. That should be freaking plenty. That's what it comes down. Maybe you need a little bit more. Maybe you go to a 4x4 slot for that 8 gigs, even though you're only going to maybe use half of it or something. But yeah, you don't really need that whole 16 on a 3 slot. Maybe an 8, not even the 4 on the 2 would probably be good enough. So, but yeah, I'm going to get rid of this. USB, we can see down here. So we went from USB 1, which was 12 meg, USB 2, which is 480, and now we're starting to get to the world of USB 3. All right. This on the left up here, that is USB 2. The blue one is USB 3. All right. So USB 3, that's blue connector by standard. I don't think it's required to be blue, but most of them are blue connectors, which might make your laptop look a little funny if you look at the side of it. Like, why the hell are these blue, random blue spots? And I think that's when they start trying to get rid of them. I think you might also see, if it's not blue, it might say like SS right here. Actually, I should put it up here. Something like that for like super speed. So if it's not a blue connector, you might see that. But if you look inside, you can see there's an ever so slight difference. We've got 4 pins here. And you do have those same 4 pins there, which is nice because that means it's backwards compatible. Like a USB 2 device and 3 device. But on this one, you also can see that we've got more pins going on back here. So we actually have 8 connectors on a USB 3 compared to a USB 2. Big benefit in that aspect for those faster connections. I mean, just look at the difference there. 480 meg to 4.8 gigabit. Holy crap. I mean, that's what? That's 10 times faster at a 0? Yeah. It's 10 times faster. From 2 to 3. And then you go from 3.0 to 3.1 and you go up another freaking double speed. You go up to 10 gigabit per second. I mean, that is as fast as what PCI 3 4x or PCI 2 8x. So USB 3.1 is faster than that. Most 3.1 ports that you're going to see are going to actually be USB-C. If you're living in a cave and you haven't seen USB-C yet, it's a connector that looks kind of like that. I am a huge fan of USB-C. I don't know about anyone else in here, but the whole you can just plug it in either way. I know Apple fanboys, you've been able to do that for a while now with Lightning, but I like USB-C. Big fan of it, and it's just it does everything. It does high power transmission. I think USB-C you can get 100 watts of power out on that one single connection, and it's not just 5 volts. It's not 5 volts at 20 amps. I think you get up to 20 volts at 5 amps, I think is what it does. And that's like a handshake between the device you're plugging in and the device that's the charger and the device you're plugging in. It initially sends 5 volts, and that's enough to power all the ICs. And the IC goes, "Hey, can I get 20 volts?" And it's like, "Yeah, sure." And it spits out 20 volts if it has that capability. It's a little bit annoying to work with, especially since it's not the best protocol, from my understanding. But that's a difference. We're talking about networking. But anyway, you can see that a USB, network connector, especially if you have a USB-C one, plenty of speed there, especially for a 1 gig network connection. I mean, even coming down to USB 3, which is again, the little dongle that I have, it's got plenty of capability there for a nice fast connection in the long run. So that's PCI and USB. USB, as I said, it's kind of taken over. It says it on the screen, but I haven't said it verbally. USB is Universal Serial Bus. So this was the old serial interface that they revamped into something new, which is really what it comes down to. This is also why everything kind of plugs into it. It's supposed to be the universal port on your computer. I think it was in here. I have too many things plugged into this computer. They've had to give me a hub, that's 1 to 4, and I've got 2 things plugged into that already. And this was plugged in, that's another 3. That's another 1. But it's between the web camera and the document cam and the keyboard and mouse and the pen input and I have a number pad up here which allows me to control the scenes of what's showing on the TV and start and stop my recording. I just have a lot of USB devices, and then when we were doing the serial stuff, I had the oscilloscope plugged in, and the Arduino plugged in. I was like, I'm running out of freaking USB ports. It's the way the game goes. Just everything likes USB, and I don't think that they give you enough USB ports on things anymore. Most people are fine, but me, I have a lot of USB devices. All right, let's jump back into the actual world of networking now. So we have talked about this already, the world of Mac. All right, and as you can see, I do have 2 different MAC addresses, highlighted there. Windows used to call them physical addresses. I'm assuming Windows still does call them physical addresses. /alt, but A. Ethernet. Yeah, this Windows still calls it your physical address. You think they just put MAC address there and make all of our lives easier? Yeah, so this really is your MAC address. Not that you guys can read that. Put it over here. And MAC stands for Media Access Control. Right? And that, again, that is assigned to your network interface card. Every network interface card has a MAC address of some. We think about that, we think about Ethernet, we think of Wi-Fi. But Bluetooth is also a networking interface in the long run. And that one also does have a MAC address. This is supposed to be unique to your device. And this is also, again, assigned at the when whoever it is that makes your device, they assign that to your specific device. So if you have a D-Link Ethernet adapter, it is saying, okay, this is a D-Link Ethernet port, and they've got this MAC address range, and they assign them to their devices. They go from there. Yeah. So this is supposed to be unique to your device. MAC address. Yeah. This is, I think, the one. So the first 3 octets is the organization's unique identifier. So that would be this. Go back. That would be this 10 to this 5 here. All right. And then the third 3 octets is the network interface controller specific. All right. So anytime Intel is giving out MAC addresses, because it's their Intel hardware, they use 10F005. Xbox uses this, and blah, 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 blah. Which is kind of nice, because that means you can look up what type of device is on your network. All right. At home, it's like you're like, well, I have 30-something devices. What is this one? Well, if you look up the MAC address, it tells you that it's a Motorola something, or it's like, oh, that's my cell phone, because it doesn't always have a name that makes sense. Is what I've come to the conclusion of. Or it's just blank. Why is there no name for this? Look it up. Okay, it's this type of device. It's most likely then going to be SY, whatever it is. Yep, so I said, here's another example, 000A959D6816. If you haven't realized this already, or you have forgotten, this is hexadecimal. Right? Hexadecimal is 0 through 9, which there's 10 possible combinations there. And then also we can have A through F in any spot, and that's another 6. Hexa is 16. So X is 6. But anyway, so you have 16 different possible combinations for every spot. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 different spots, and we could have 16 in each spot. That would be 16th to the 12th power. And that gets you this wonderfully ginormous freaking number up here, which is what, million, billion, trillion? 281 trillion different possible combinations. That's a lot of freaking devices. I'm actually curious to know how many MAC addresses of that trillion we've assigned to things. Because if Intel has this large section, think about how many billions of devices sold every year. Your VR headsets, Oculus Quest 2s or whatever it is.
Let me ask a question then. So every device that was made have an address to it, right?
Yes.
You can't reassign that address, right?
Well, you can. So as we were talking, again, this is old school. This is locked to your device. So Intel says, here's your MAC address, and in the long run, there's really very little need for you to change it. It's not like, oh, I'm going to increase my, I'm connecting to a different network. I need to change my MAC address. You don't really need to. All right. So it doesn't really matter.
They'll know where you're here.
However, what has changed in the recent past, and we'll come back to the slide, but let me just go to the next one, is for safety purposes, Android and iPhone has allowed you to do, they call this, Apple calls it a private address, and Android, I don't know what, it's just, you know, I don't remember, I don't know what it says behind that window. These are images I got off the internet. But they allow you to actually change your MAC address based on the Wi-Fi that you're connecting to, with the whole reason being security. You know, we are tracked 24/7. Not just like Apple's tracking your. You connect to Starbucks Wi-Fi. They're going, hey, look, this MAC address showed up at Starbucks Wi-Fi. You connect to HTC, and they're like, hey, look, this is your HTC device. Some like companies can even tell you what room you were sitting in, you know, based on, well, there's the Wi-Fi adapter, that little square up there in the ceiling right by the yellow power, the Rubo on it, that's our Wi-Fi. So if your phone's connected to that, they know you're within so many feet of that Wi-Fi. And so they know, okay, you're you know, in this location. And if they're really good, they can say, that one's tracking you, another one's tracking you, another one, they can figure out which one you're closest to and then kind of triangulate your location to get actually much closer. I don't know if HTC has this capability, but it is possible to do. So to help restrict that, where your phone is actually saying, hey, I can do a random MAC address type of thing. So it's every time you connect to a different Wi-Fi name, you have a different MAC address. So it's harder for, say, you know, Starbucks to say, oh, this is Tim at our store today. Like, oh, well, my phone connected this today and that tomorrow, and you know. I don't know if it's daily changing the MAC address or it's just every time you connect to this Wi-Fi, you have this MAC address. I haven't looked into that. But they're allowing you to change it for helping prevent people from tracking you as easy. I'm not saying they're still not tracking you. Because just like with HTC, and how many of you guys have signed on to the HTC campus Wi-Fi with your phone? What do you have to do? Type in your username and password. That puts a little token or a little certificate on your phone saying, that way you don't have to do it every time. It says, hey, here's my certificate, my permission to get on the network. Well, even if they're not tracking your MAC address, they can track that certificate to say, oh, I'm looking for Trevor. Trevor's certificate is on this phone today. This phone is in this room, you know, type of thing. So there's a lot of tracking that can be done, which is very freaking cool. You know, if you don't want to be tracked, go live in a cave in the middle of the woods. That is your only option. You can't even live in the woods because what flies over your head daily? Satellites. So you've got to live in a cave. That's your only option if you truly don't want to be tracked today. Think about how many security cameras and things that you walk past every day. And there's nothing stopping them from running facial recognition on that. Nothing. If you're in public or a private location, you've basically given them your consent to be on video. You know, they're allowed to collect that data. But anyway, so that's what the MAC address is. Can it change? Yes. Is there any only good reason is for your security or safety tracking capability? That's why we're changing my Android and iPhone. I think Windows laptops might even not be able to do it. I'm not positive. I haven't looked into that one. But again, there's no real need to change. It's not like, oh, I'm on a different network. All right, let's go back. So, yeah. Where was I on this one? So, as I already said, manufacturers have their assigned pool of devices they assign. I would just assume they just go in order. You know, year 1, year 2, year 3, year 4, year 5, year 6. I don't think they're like jumping around. I don't see any real benefit to that. As I said, you can look up a device based on its MAC address. DNSchecker.org/MAC-lookup option for you. And that is somewhere you can just go type some things in. What's this? DNSchecker.org. DNSchecker.org. And that will look something like this. And then you can type them in 00:0A:95:9. 168:16. And that tells you that this was from an Apple device of some sort. And like they even tell you the start address and the end address. So you can see that their Apple has from 000A95 zeros through Fs. So that is the Mac pool range. Just kind of one of those interesting things to be able to do for whatever randomization. Now, what does change, and this is going to come a little bit later, but what does change when we are asking for information, right? When we're asking Amazon for information, we put our whole packet of information together that we're sending. The MAC address every hop is changed. When I say, hey, I need to get to Amazon, so from here to the server on campus or the router takes my MAC address off and puts its MAC address in its place, and then transmits information to the next step. That takes its off and puts its in its place and transmits. So that way, when information is getting passed back, it knows, oh, I need to send to this MAC address. So that's how it's kind of allowing the hops to work. We'll come more back to that in the future. Depending on if remember the whole OSI level thing? We have 1 through 7 of those. Right? I know, not my favorite topic by any means. The OSI model. But MAC addresses are used on level 2 of that for broadcasting. IP addresses are used on level 3 for broadcasting. That seems like redundancy. But it's just kind of something that you need to just kind of be aware of. That's all my notes. All right. So back to IP addresses. We have talked about them to some extent. We've kind of broken them down, those types of things. But here we have some different classes. So Internet IP version 4 versus version 6. I do have 2 examples here. Back. So IP version 4, out of 4, and this one right here is a 6. Look how much longer the 6 is. I mean, A, B, C, D, E, F, O, 1, 2, 3, 5, 7, 8. So there's 16. So there's another A, B, C, D, E, F, O, 1, 2. That's another 16. That's 30 freaking 2 different spots that you can put a hexadecimal number. So again, that would be 16 to the 32. That's a lot of combinations. Right. That's 340 undecillion. How many freaking zeros that one is? So that's a lot. But anyway, IP version 4, which is what most things nowadays are using, especially small and large business internally. Externally, that's when you start getting into the IP version 6 actually being a necessity. Internally, not really a necessity. But you can see that we've got 5 different class ranges. So we have 1 to 126, that's for your large enterprises and government agencies. 128 to 191 is your medium-sized business and organizations. 192 to 223 is your small entities and home networks, and 224 to 239 is your multicast. And even that we actually then break down into a few more different categories. There's also what's called private and public. I have that. I don't really have that listed up here. You also do have private IP addresses, and then you have your public. So your private, that would be like your home router. That would be that 192.168, kind of the most common. Another common one is 10.0.0. Or I think it's just 10. I think after that. But yeah, so it's kind of a crapshoot. Most of these IP addresses. So unless you're going to truly get into a network field, you don't really need to understand all this in super depth. But again, I'm trying to introduce you to it so you at least have a good background for all of this when you see it in the field. Because there's one thing I've learned is be nice to the IT people. All right. Yeah, I had that old computer, not old. It was a brand spanking new all-in-one computer. It had 6 cores, 12 threads, 16 gigs of RAM, and I went to IT and I said, hey, my computer's being slow. Can I get a new one? Within a week, I had the new desktop tower, these 2 beautiful, I don't know what like they are, 20-something inch monitors. She brought me over the hub and everything else that I needed to get up and running, how I wanted to be set up and whatnot. And, I mean, like, within the week, like I was like, yeah, I was expecting still, yes, we'll get to you at some point. And I wasn't in a huge rush, but this is definitely more how I wanted my teaching setup set up. I think it's actually working pretty well. I don't think capability-wise this is that much better than that all-in-one. Like if I look at my specs, I think there's still only 16 gigs of RAM and is that going to show up? Yep, 16 gigs of RAM. I still only have a 6-core 12-thread processor. Maybe a turbo's a bit higher. I don't know. I do have a real GPU though. That's a big benefit. That's not a little integrated one, but be nice to the IT people. I've in my time, I do anything I can do myself. Just do it. Right? If I don't have to ask IT or facilities or anybody to like when I got this, they're like, what software do you need? I'm like, just give me the basic install. I'll install everything I need. I'll do it. They're like, cool, all right, yeah. I just saved them probably 2 hours of work of random, I gotta go find the downloads for this software, I gotta find that one, I gotta install it. I do them a favor by not making them waste their time because I can just sit here and do it while class is running. You guys are working on labs, I can go click on install and I can help you guys and come back and click on another install and keep circling that. But I've just learned, anytime you can do something yourself, just do it. You gotta be a little careful not to step on people's toes, but that's more of a union issue than anything else. But anyway, yeah, so I like to, get you guys nice and up on this. Yeah, so back to the whole IP version 4 verse 6. IP version 4, if you guys remember, there was 4.3 billion different possible addresses. Right? Even if you're doing a small private of 192.168.0 or .x, you still have 255 different possible 256, possible combinations there for your small home network. As we kind of roughly counted last time, no one's even near 256. I think I'm the closest with like 40 or 50 devices, maybe. I don't even have that many. I know I counted, I think, 30. So I have a lot of devices on my network, but it's not like stupidly anywhere near this, so it's not going to be a problem for me. And even so, then you just say, okay, I need to change my subnet to add one more digit, one more little spot here for it, and now I can go up a whole nother step and double that, 512 combinations now. So very easy to extend your capabilities if you truly need to. Yeah. All right. So IP addresses are a number used to label any device connected to a network in which the Internet Protocol is used as a medium for communication. So if you're doing any IP stuff, that's where the IP address comes in. It's really good too. And one of the big benefits of IP addresses over MAC addresses is keeping the network cohesive. Right?
Again,
keeping the network cohesive. If we did this based purely off MAC addresses, and you're like, every device comes from the factory with a unique MAC address, like this Ethernet dongle has a unique MAC address. Why do I need to assign IP addresses? This is its own special, unique thing. It's already different. Why do I need to assign a new one? Well, again, back to that cohesion. If we all got onto a network purely based on MAC addresses, and I've got Apple, and you've got Samsung, you've got Motorola, you've got a Google phone, we all have these different phones, well, that means our MAC addresses are going to be all over the freaking place. By going to IP addresses, we can now group all of those devices into one network. So when I say, hey, I need to talk to all the phones, I can go, they're on this network, and I can send a broadcast to that network, and it's going to broadcast just to those phones. I don't have to go broadcast to phones and now do this wonderful game of lookup of going, are you a phone? Are you a phone? Are you a phone? No, I can just, when you connect, I can say, you're a phone. I can put you on the phone network or the phone Wi-Fi, and you're on the laptop Wi-Fi, and you're on the mobile cart Wi-Fi. You can separate devices that way or by VLANs or other ways to group them logically. So It's just like you guys are in ELE 101, section 01. It's like me giving a section number to a class. It just makes my life easier for grouping things. So that is one of the main reasons that we use IP addresses. It allows us to group things into broadcast domains or other specialty interests. So back to the student Wi-Fi can't connect to all the network servers on campus. So if I have, or license servers, sorry. So for like my automation studio or my PCIe portal for my PLCs or robots or whatever, your Wi-Fi doesn't access that. So even if you have your laptop out and you've installed the software, you still can't get a license off our server. And HTC is on that for security purposes. But if you're on the mobile cart Wi-Fi, you can, which is where all the laptops in this room are. So again, security is another reason. It allows us to group things in logical ways. It's a long one. Kind of nice. All right, so subnetting. We've talked about this. We're going to come back to it. So the subnet here, this /24, that is really what is telling us what a subnet is. And what a subnet is taking a network and splitting it into smaller networks. All right, kind of like streets. All right. So this 24 tells us how many binary bits we have that are ones. So 255, 255, 255 would be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Keep saying ones, right? It's a lovely thing to listen to me talk about. All right, I've made my 24 ones, and then the last ones would just be zeros. All right. So anywhere you see a 1 above it, that is my subnet. All right. And yes, you do actually have to take these down to binary if you're truly doing networking things, trying to figure out subnets and those types of stuff. It freaking sucks. All right. When it's nice, when it's 8, 16, or 24 as your subnet, life is easy. When you start getting beyond that, life starts becoming a little bit more freaking difficult. All right. Which you'll see down here at the very bottom. So by looking at that, we can see that the first 3 octets here are all our network portion. So we look and we go, that's 192.168.52. And then our devices, wherever there are zeros, is 126. All right. Now, back to my okay, that only allows, again, 256 different possibilities. You have one broadcast. You have, a few others that are already taken up. So, let's just say you have 250 devices that you can get on this network. Well, maybe you have more than that. So how do we go get more possibilities? That's where the whole wonderful world. You could just go down to a /16. You could say, okay, we're going to do /16, which makes 192.168 the network portion, and that would make 52.126 the device portion. And that would really, really skyrocket your possible combinations here. But maybe that's not actually what you want to do, because also that puts everything again on the same network. So everything can talk to everything else. So maybe having one network, say for your home automation devices, and one network for your desktops or whatever. So that way your home automation devices can't talk directly to your desktops. They have to talk to the server, and the server then talks to your desktops, because there's no need for your home automation devices, which could be security risks, to directly talk to your desktops. Or you have your home automation stuff set up, and you've just said anything on this network can't access the internet. Because, again, it could be a security risk, because home automation devices are horribly known for not having good security. Firmware doesn't get updated, hacks get found for them. All of a sudden it's like, yeah, every Wi-Fi camera from this manufacturer you can just basically remotely access with this little script. There's entire websites out there for unsecured security cameras, where you can just go watch the feeds from all these things. And, kind of an interesting thing to look at if you're prepared to look it up. But anyway, if you want to put them all on the same network, you would have to say, okay, I need to change my subnet. So we went from 24 down to 21. So I want you guys to tell me, what is the network portion of this? What would be our network address? All right. And if we look up here, we can see all the ones. So everything would be all of those, which is why we have 192.168.52. Right? since we're lowering that 24 down to 21, we're losing some digits here. And those all just become zeros. So I guess the real question is, I'm going to give you guys a few moments. Try to convert 00110000 into binary. No, not binary, decimal. So go ahead and take a few moments. All right, so how do we go about converting binary to decimal? You guys remember my little talk, I don't know how long ago at this point. But the first thing I like to do is just write out my 8 spaces. 3, 4, 5, 6, 7, 8. And then I go ahead and I write numbers underneath them. So 1, 2, every time it doubles. So 4, 8, 16, 32, 64, 128. And then you just go write your numbers over them. So it would be 0, 0, 1, 1, 0, and then the last 3 are zeros. We go ahead and we just have to do a little bit of math. You just multiply up and down. So 128 times 0 would be 0, 0, 32, 16, and the rest are zeros. And then we just add them together. So 16 and 32 gets us to be 48. All right. So our network portion now would be 192.168.48. All right. Now, this does make the device ID now not quite as simple, right? Because it's not just 126 now. It's now, 4? So it's now going to be, and it's now, it could be, it could be 1, 2, 3, 4, 5, 6, or 7. So it could be 1 through 7, dot, and then 0 to 255. So our device ID now just has become a lot more complicated. But basically, we just added 3 more bits of information to our network, our device ID. So we're going to add 256, 512, and 1028. So we now have 2,056 different device possibilities that could be on the exact same network. That's ridiculous, if you ask me. That is a lot of freaking possibilities. So, subnetting, it is a great tool. It is also a very confusing tool. All right. Yeah. Back to the, y'all aren't network professionals. I'm not expecting you to do this on a daily basis. But if you're ever like, okay, let me get this, this on the network, and you go, hey, IT, what's the IP address? And they just ramble off 4 digits to you. Most likely they're going to tell you a subnet, but you might just, ignore that. And then you're typing things in, you're like, oh, subnet 255.255.255.0, and then it doesn't work. Because you're not on the right subnet, it's not on the right network, then it doesn't know how to communicate properly. So it is a very important aspect. The other thing that we haven't talked about yet is when you're setting up a computer, you should have 4 pieces of information. You're going to have an IP address. You're going to have your subnet. You also will have what's called a default gateway, which is if I don't know where to send information, this is where I send it to. All right. And then you also may have your DNS. Now that one isn't truly necessary, but it is nice to be able to say this is the DNS I want to use. On a quick side note, there are what they call DNS ad blockers.
DNS
ad blockers. Like if you're browsing the internet, you go to, again, Amazon.com. You know how, not Amazon, that's a bad example. You go to weather.com. You just look up the weather, and they've got all that, the Amazon link, little ads and things like that. Mm-hmm. Well, Amazon has its own little, it's like ads.amazon.com or something like that, which is what makes that little thing pop up. And a DNS ad blocker, when your computer says, hey, DNS server, where is this website? You go to this DNS ad blocker first, and it says, oh, that's ads, and it just sends like a 0.0.0 back to you. So when your computer then says, hey, I need this information, it never gets it. So either A, just displays a gray square that nothing, there's no ad there. Still takes up the space, but there's no ad anymore. Or if it's a If you're really lucky, that little thing just doesn't show up on the web page at all. So it's a very handy little ad blocker. So another little way to add some security to. So we're going to come back to DNS again in a few minutes. So why do we have MAC and IP? So we've kind of already talked about this. First one, it's easier to group TCP/IP addresses because we get to assign them. So when you get on my network, I say, you're no longer Frank, I'm going to call you George. And you're George 1, and you're George 2, and you're George, whatever the case is. It just makes us easier to group those things. So that is one reason that we like TCP/IP addresses over MAC. Also, we could, in theory, get rid of MAC addresses. Yes. All right. But the standards nowadays are written with them included, so we'd have to rewrite like everything. I always say we should move away from the standard measurement system, the U.S. imperial measurement system. I freaking hate it. We are one of the few countries to use it. Basically, everyone uses metric. Let's just go to metric. All right. And I say it would take like 3 generations to truly get to the metric system. Because you have the generation now, all of us are like, screw it, I'm not learning a new thing. I'll have our next generation who are used to the parents saying, screw the metric system, we like imperial better, but they're learning the metric system. And then after that, you're basically at the metric system. It's going to take 3 generations. It would take actually, in theory, it would probably take less time to probably get rid of MAC addresses and change IP protocols around because computer hardware dies a lot quicker. Let me phrase it. Most computer hardware dies a lot quicker. Right? You go into some industry places and you're like, you still have a Windows XP computer here? Like, what are you thinking? Or is that DOS? All right. So it might be able to happen quicker, but yeah. All right. Despite the vast majority of protocols, some protocols are still in use and they rely on the MAC addresses. So again, can't quite get rid of them yet. And this allows more flexibility in the future. Those are kind of our big reasons why. But anyway, as you can see on here, you see how that MAC keeps changing. I wish they would have changed the color with it every hop. That would have been pretty slick. But yeah, the MAC address just keeps changing. So it's like, hey, this is who sent this packet, basically. This is who I am, send it out. Oh, okay, I got it. This is who I am, send it out. Goes to the next stop, the next stop, the next stop. All right, so as said, we've already talked about DNS, but we're going to hit it up again. So this is basically our phone book. All right, this is the phone book for the internet. All right, this is obviously over here. We've got a little ad advertising 1.1.1.1 as your DNS. I think Google's is 8.8.8. I have no clue who OpenDNS or VeriSign is. I don't know where those are, but here's Google. Yeah, 8.8 or 8.8.4.4 is also Google's. But this is what takes the website names, the URLs, the universal reference links, I think it's links, and allows them to be converted to IP addresses. So again, in your phone book, you've got Frank stored, and then it says that it's 496.381.75309. This makes our life easier. And I don't know about you guys, but it's much easier to remember a word than it is to remember random numbers. All right. Even so, most people could probably memorize, phone numbers, which are 10 digits. You could argue that IP addresses are only 4 digits, unless you're IP version 6. That's a whole different game. But there's only really 4 digits to an IP version 4. It's first octet, second octet, third octet, fourth octet. It's just a bigger number. It's not 3. It's like how you remember phone numbers. 317. It's like 317, 317, whatever the case is. So we could probably memorize the IP addresses if we had to, but why when we can just use our little DNS to look them up? Yep, so you can choose which DNS you're going to use. As we talked about, that 4th field. It's not even necessary to put one in because if you send a DNS request out not to a specific one, your ISP will normally pick the one that it wants to. That it's probably getting paid to send you to. So a little bit of choose there, options there. And here you can see the, I don't know if these are ping times or this is just break this. Oh, this is wiggly on me. Anyway, you can see the ping times, or I don't know if this is how long the query request took, but here's 1.1. Look, it took 13 milliseconds compared to the 22 of Google. They're trying to advertise themselves as the fastest DNS resolver in Earth. So I don't know how true that is. But let's be honest, you're not going to truly notice a 9 millisecond difference in time. So, all right. So this takes us to TCPIP. This is Transmission Control Protocol and Internet Protocol. That's the IP portion. This is the de facto global standard for internet and host-to-host layer implementation of internetwork applications. And this is just because of the popularity of the internet, which is wonderful. Again, having consistency everywhere is great. Right? We have already talked about the OSI model. Maybe I need to flip-flop my presentations. So it is based on that, which is the Open Systems Interconnection. And this was developed in Europe by the ISO, the International Organization for Standards. This is kind of interesting. If you guys remember, the internet was based on the ARPA model, right? So here we have the ARPA model, and you can see how their layers stack up to the OSI and where TCP/IP is there. So they're on TCP, which is your transmission control protocol. Then you have your IP. This is your IP address, which is on layer 3. And if you guys remember your MAC address, that would be on layer 2 right here. All right. Just kind of nice to be able to see that. A note here, TCP/ID does not include OSI layer 1, but it does rely on it for access, right? If we don't include layer 1, which is physical, what did physical include? You know, the devices, the connections, the wires, the power cords, you know, it relies on all that. So if we don't have a physical connection, you know, devices or whatever, obviously it's not going to work. So it doesn't include it, but it relies on it. Kind of weird, isn't it? All right. So the Internet Protocol layer, which would be layer 3, its primary responsibility is to routing packets from one host to another. We have what's called Address Resolution Protocol. This is called also shortened down to ARP. And this is used for the translation of an IP address to a MAC address, such as required by the Ethernet. You also have reverse ARP, which is the reverse address resolution. And this is the complement of ARP and translate hardware address to IP address. So IP to hardware, or hardware, IP to Mac, or Mac to IP. Right? You guys may remember, I said last time we talked about Mac and IP addresses, your router may assign your IP address based on your MAC address. So it's going, the first time you connect, it's like, I haven't given IP address 110 out to anybody yet. So your MAC address now gets 110. So every time you connect back home, you always have 110. Some of them, they don't care. They're just like, oh, new device. You get the next available number. Doesn't matter if it's been used or not before, as long as it's not currently being used. You may hear the term ICMP, which is your Internet Control Message Protocol. This is a protocol used for exchanging control or error messages between routers and hosts. All right, then we also have TCP. This is Service or Host-to-Host Transport Layer. All right, so again, we're now on layer 4. All right, this is responsible for the data integrity. So is the data being transmitted getting there accurately? All right, and we have 2 different ways of doing that. Way number 1 is User Data Protocol. This is UDP. This is a connectionless or unreliable protocol used for higher layer port addressing with minimal protocol overhead. So if you want something done quick, but you don't care how accurate it truly is, this is your protocol to use. All right. Your other protocol is TCP, Transmission Control Protocol. This is a connection-oriented protocol that offers a very reliable method of transferring a stream of data in byte format between applications. So that one, you do care about data integrity. All right, like is the information actually getting there? Type of thing. All right, so here you can see the TCP connection. So the PLC sends information to the VFD responds right back to it. All right, so there's that connection oriented. Like, is this a good connection? Did you get my request? All right, this would be like pinging another computer saying, hey, are you there? And it goes, yep, I'm here. All right, the other option is UDP, and you can see the sensor is sending data to the PLC, and it doesn't give a damn if it actually gets there. All right, it's like, hey, here's my temperature value, or whatever the case is. Hey, here it is again. Here it is again. It just, constantly is sending that information. All right. This does have the benefit of being lower latency because all we do is send. Right? The PLC isn't going, hey, what's your temperature value? And you're going, oh, it's this. All right. It's just, here's my temperature. Here's my temperature. Just sending it out. It's been programmed just to transmit. So both of these work. It's just TCP is a little bit more reliable. UDP is a little bit faster. In industrial environments, sometimes speed is a necessity, right? So maybe UDP is the more preferred one. But maybe you have a lot of EMF noise or something, and you have a very unreliable connection between your sensor and your PLC. Maybe you have to use TCP to make sure that that value is actually getting transmitted back and forth. So again, there is a lot going on there in the long run. That's super important. So it's just like, okay, which method are we going to use? Most of the time, again, you don't really have the option. It's, I'm setting this up, and this is my choice, because that's the only choice there is. But just know, TCP is one, UDP is the other. All right, we're getting to the end of this. Network frame. So when we are doing a TCP/IP connection or a UDP connection, this is what we get sent over the network. So we have our local network header, which would be our first section. Then we have our IP, then 2CP or UDP header, and the application data, and then the trailer. So that has 5 different parts. The header and trailer can change depending on the network type you're on. So whether it might be wireless or wired, or fiber optic, or maybe you're on a coax connection, or DeviceNet, or whatever the case is. And again, this is not specific. This isn't towards DeviceNet, but this is based on networking. That's what's going on. When we are actually transmitting this data, the IP datagram, the IP header, is not touched unless the network requires smaller packets. So, suppose say your network allows 32 bits of data to be transmitted. Well, if you're all of a sudden changed to a different type of network, because you're trying to go a long distance and they only use 16 bits, because that way if they lose one, they only lose half as much data. You then might split that IP header up into separate sections. Then the packet might change what it comes down to. But overall, our IP header here is not changing at all. Back to the whole MAC address. The MAC address changes, the IP header does not. All right. Whew. So here we have the IP portion. So this is responsible for delivery of your packets. This is, as I'd call it, the equivalent of the postal service. All right. You put the IP at your mail in the mailbox, and then the postal service gets it from point A to point B. All right. It's going to forward and route and deliver datagrams on the basis of IP address attached to the datagrams. So I've been misspeaking all of class today. I can't believe I made that simple mistake. But the IP address is where it's trying to get to, not where it's coming from. I've been saying it's where it's coming from the whole time, but no, this is the where I'm trying to get. I screwed that one up the entire class, but that's okay. We just fixed that. So again, same idea of how post service does this. So you have your address on there, and the post office first goes, what's the zip code? Kind of gets it to the right location, and what's this? And then it gets, keeps kind of separating things down. IP is also what is responsible for fragmenting those datagrams if necessary. So again, if we're going to some network that requires a smaller piece of information, it's going to then be the one that says, okay, we need to divide it up this way, type of thing. Ethernet can handle 1,500 bytes, but can only handle, but I guess a 0.25 connection only handles 576 bytes. So an IP header is a minimum of 5 32-bit words. So up here, you can see our 32 bits. So you can see where bit 0 is, bit 32, right in the middle 16, and what's going on with all those. And we have up here, we actually have 6. Notice the last one at the bottom is Options. So that one is the one that's not necessarily being sent. Everything above that is, or at least we're sending those bits. We might not say that's necessary. We might ignore that section, but we're still sending bits in that place. So the VERI, V-E-R-I. This is the version of IP being used. No surprise there. We have gone over time and we have changed IP versions, right? It has progressed. It has changed. It's gotten better, maybe. All right. Some might say it's gotten worse. I don't know. But yeah, so we are progressing. So that is what version we're using. So that way all the devices just know this is the format of things. Then we have our IHL, that is our internet header length. And this is important since that header can be different lengths. That just gets really annoying, doesn't it? And so that's, again, do we want 532 bits? Do we need 632 bits? How many messages are we sending, basically? And that's what the IHL is telling us. Then we have our type of service. This informs the network about the quality of service required. So back to you're transmitting information to Amazon. What's important to you? Is the minimum delay important? So, get this packet to there as quick as physically possible. Is the amount of throughput, how much bandwidth do we have getting there? Like, I might need one small packet to get there instantly, but I'm transmitting 12 terabytes of data. It's more important to me that I have a constant stream than an extreme speed. So that could be that one. Reliability, I need this to not have errors on highly sensitive data, whatever the case is, or the minimum cost. All right, so that's your type of service. All right, the identifier, which would be this one, that is unique to each datagram sent by the host, and this is kind of like the tracking number you get from the post service. So again, you're setting this and going, hey, here's my tracking number. We have fragment offset, which is used in case of fragmentation and used to reassembly the datagram. That makes sense? Time to live, or TTL. This is to ensure that undelivered datagrams are eventually discarded. So you sent one, and it went on 40 or 50 different hops to go from point A to point B, and it took 20 times longer than it was supposed to. And it's going, hey, I just got this information. And the time to live is basically saying, oh, that's old. We don't care about that anymore. The data's already been retransmitted. I've already received it another way. Whatever the case. Like, oh, you took a detour, and then the next, 30 seconds later, the main highway opened up again. So you're on this long, winding road detour to get to point A, and you're like, that point A is like, they never arrived, send it again. And then the next time they send it, it's straight down the highway. All right. So that's our time to live. Protocol is the next level protocol header, presents the data portion of the IP datagram. So you're going to see 1 for ICMP, 6 for TCP, or 17 for UDP. And then our last one is checksum. So this is making sure that we don't have errors in our header. This only checks the header section, so these first 3 bits. It does not check the source address, the destination, or the options and padding. Whew. We all confused yet? All right. So you should kind of have a good idea what these are. I'm not expecting you to know perfectly. You should have a decent idea what these things are. And then here, what I've got for you guys is a list of standard ports. We talked about ports last class, some about how on port 80 is HTTP and port 443 is HTTPS. So depending on which port you're trying to tell your information to get to, it depends on which window or door in the building that information is going to get sent. All right. This is just some of the kind of frequently used ones. This was a much longer list that I cut down to just this section, just to make it nicely fit on the page. But I'd say these are some of the pretty good ones that you're going to see. As I said, HTTP you'll probably see, HTTPS you'll definitely see. 22, that is our SSH. If you do any remote logging in via command lines, that's where you're going to be. DNS, that's on port 53. Here you go. Let's see. DHCP, you're going to see those. That's having to do with getting your IP addresses. So that one will be important. SQL Server, that one's going to be important. If you guys remember talking about SCADA and how SQL now has kind of become the king of data storage, so that port might be important to you. And the key here is not necessarily that the port numbers are actually important to you, but that they're open is the important part. Because it's like, I need access to SQL Server, and that port is blocked, and it's like, why can't I access it? Like, I see the IP, I see the computer, it's literally right here next to me. But for again whatever reason, IT has a port on there, saying, oh no data is allowed to access port 156. It's like, I need access SQL. That's port 156. You just have to get IT to open that one port up, and then everything should probably work fine from there. And this is one of those reasons why all of the stuff that we've talked about today, and even though I keep telling you guys, unless you're going into the IT field, this isn't super important. Being able to have that intelligible conversation with IT is the important part, because you're going, hey, I'm having this issue. I know it's working because if I'm locally on the machine, it works just fine. But as soon as I leave that computer and go to a different one and try to access it, it doesn't work. And you might, that's starting to be like, okay, so it is a networking problem. And how does this work? And understanding how your network communication, those types of things work, is going to be important. So yeah, you're not IT professionals. You're not going to be the ones setting all this up like individually. But back to that, like, you want to make them do as little work as possible. The less work they do, the happier they are with me. And the happier they are with you, the more likely they're to help you in a quick manner, and B, when real problems come up, they're going to jump right on it for you. That's my theory. So yeah, understanding that, hey, if there's ports and things like that in the background, it's definitely going to be very helpful. All right, and that is TCPIP.